So far, we have been looking at the motion of a single particle or a collection of particles, but only that of its CM, that is the center of mass. So, for example, if we have a collection of particles like this and I apply different forces on each particle, and suppose this happens to be its center of mass, what we have been looking at is how the center of mass moves. That is, the equation that we had been solving in the previous lectures was the total mass m r cm double dot, where double dot refers to the second derivative of the r vector, is equal to total force applied, where m is the sum of individual masses, that is the total mass. The vector RCM is defined as 1 over m summed over mi Ri, that is a vector for each individual particle, and F total is the net force being applied on the system totally. Now, I want to look at individual particles, how its motion takes place. I want to go beyond the center of mass motion. So, for example, suppose I have these particles connected by a spring. For simplicity, I will just take 3 of them and I apply different forces on each particle. Let me name this particle 1, particle 2, particle 3. Let force on particle 1 be F1, let force on particle 2 be F2, and let the force on particle 3 be F3. As we apply these forces, in the next instant I could have a different situation in which the particles could be, maybe the spring has stretched. This, let us say, is a rod which is cannot change, and maybe this spring has stretched. Further, it could have changed its orientation, that is, if this is particle 1, 2 and 3, other situation I could have is maybe particle 1 is here, particle 3 is here, and this is particle 2. In other words, under the influence of these forces F1, F2 and F3, the body could deform, that is, the distance between the particles could change and it could change its orientation. Nonetheless, the center of mass still moves according to what the net force is, that is, the center of mass would still follow this equation. But in addition to that, the translation of center of mass, like a heavy point particle, under the net force, total force F total, there could be other things, and that is what I said, maybe the deformation, maybe a change in orientation. So, these are beyond the translation motion of center of mass, and this is what we are going to focus on. To start with, let us again separate the deformation motion and the change in orientation motion. So, I am going to make an assumption and this assumption defines what are known as rigid bodies. The assumption is that given a system of particles, when I move them, so let me again number them 1, 2, 3, 4, 5. When I apply different forces on each of the particles, the distance between two particles remains unchanged. These distances remain fixed. Similarly, distance between this and this, distance between this and this particle, and so on. In other words, in the previous example where I took one rod, one particle here, and there was a spring here, I replaced this spring by rods that cannot change their length. So the distance between two particles would remain unchanged. You can feel right away when I apply a force, it is not going to deform. The only thing this body can do is change its orientation. So for example, 1, 2 and 3 could go to a different shape like this, different orientation like this, and this is known as a rigid body. In a rigid body, the distance between any two particles of its body remains fixed, and the only possible motion then is translation of center of mass plus a change in orientation. This is how we simplify the problem. The deformation part we can add later. For example, deformation leads to, say, wave motion or plastic phenomena or extension and shortening of say spring under a force. We are leaving that right now. Right now we are going to assume that the body is rigid. Take as an example again a body consisting of two masses which are attached to a rod of fixed length L. So I would call it a rigid rod, and this is a rigid body. Now if I apply a force here and a force here, let's call it F1, let's call it F2, what will happen is F1 and F2 have a net force. Let's say this is F1, this is F2, so this is a net force. So center of mass of this body would move in this direction. It would have moved, so center of mass would move, but the body could itself change orientation. It could be in this orientation. In general, I would require three variables to describe translation of the CM and three more variables to describe the change in a rigid body's orientation. You can think of these three variables to describe the change in a rigid body's orientation as three angles from three axes. So in general, what we learn is need 6 variables to describe the general motion of a rigid body. You may ask, why 6 only? In a rigid body there could be 10 particles, 15 particles, 10 raised to 23 particles. Why only 6? That comes because there is a big constraint we are working with. The constraint is no matter how many particles, the distance between two particles will always remain fixed, and that constraint reduces the number of variables that I need to describe the motion of a rigid body to 6. 3 of these are for translation and 3 for rotation. What will happen if I take a rigid body? Now I can make it a general rigid body like this. All the distances are fixed between these points, and fix one point of this body. Suppose I pin it here. then it cannot translate anymore, and therefore, I would need only 3 variables for describing its rotation. So, I hope by now I have given you a feeling of what a rigid body is and how many degrees of freedom does it have when it moves. It has 6 degrees of freedom. On the other hand, if I fix one point, then it has only 3 degrees of freedom, and that is the change in that angles required to describe the change in its orientation. So, that is the rigid body, and in next few lectures we are going to make this approximation that the bodies we are considering are rigid bodies and describe their dynamics. We start with simple problem of rotation about one axis, then we let the axis also move, and in the third case we also let the axis change its orientation. So, these are slowly we are going to build up these problems, but we are not going to consider the deformations. In that sense, all the body motion that we are considering are rigid body motions. How about the dynamics of a rigid body? You recall, when we considered the dynamics of a particle, we started with second law of Newton that said that for a point particle, force equals the mass times r double dot, or mass, the second derivative, the acceleration of r with respect to time. Later, when we learnt about momentum, we said force is nothing but dp dt, that is the rate of change of the momentum of the particle. The equivalent role that is played in describing the orientation of a body in rigid body dynamics is that of angular momentum. That is the role that momentum plays in linear motion is played by angular momentum, and let me denote it by a vector L in describing rigid body dynamics. Angular momentum is a general concept, a general quantity that could be defined for any motion, and but it is particularly useful in describing rigid body dynamics. So, in the next few minutes or maybe the rest of the lecture, we are going to spend time on understanding the angular momentum. To develop the feeling for angular momentum, we are first going to start with definition of angular momentum and then going to describe it for a single particle. So, given a single particle moving in coordinate x, y and z with origin at O, suppose there is a particle moving like this with velocity v, its mass is m, then the angular momentum with respect to O, and I emphasize with respect to O because angular momentum happens to be an origin dependent quantity, is given as mass r cross v, where r is the distance displacement of the particle at any given time. This is the definition of angular momentum for a single particle. How about the dynamics that I was talking about? The change in angular momentum with respect to time, analogous to what we learn in single particle dynamics as change of the momentum with respect to time. Here we discuss change of angular momentum with respect to time is going to be equal to the derivative m r cross v. I am now going to use the chain rule for differentiation. For those of you who feel little uncomfortable, I will leave it as an exercise that you take the components of this cross product vector and do it in terms of component, but I am going to write it directly as m dr dt, that is I take the derivative of r with respect to time cross v plus the second term, because I am using the chain rule, m r cross dv dt. As I said earlier, if you are not comfortable with using the vector quantities directly, take the component of r cross v, maybe take the x component, which would be equal to y vz minus z vy. Take the derivative and see that finally this emerges. So, derivative of r cross v is going to be dr dt cross v plus r cross dv dt, m is common. So, what we have obtained is dl with respect to O dt, where let me just remind you that I have an origin O, x, y, z, particle is moving like this with momentum p, this is r, is equal to m dr dt cross v plus m r cross dv dt. But we know that dr dt is nothing but the velocity itself, and velocity cross velocity is going to give you 0. And therefore, what you are left with is this quantity. In this dv dt, the derivative of velocity with respect to time is the acceleration. So, I have d LO dt is equal to m r cross the acceleration. M times the acceleration is the force, and therefore, this is equal to r cross f. And we define this quantity to be the torque, and I am going to denote it with this symbol called tau. So, what we learn, and I have derived for you, is that given a particle moving, the change is in its angular momentum, and I always denote with this O, emphasizing the fact that angular momentum is a quantity that depends on the origin, is equal to r cross f, or the torque about O. Notice, while deriving this, I use the fact that f equals ma, that is force equals mass times acceleration, or the second law. Except that now, instead of talking about change in momentum, I am talking about change in angular momentum. Are the two equivalent? So, question we now have is, question is dl dt equals tau equivalent to f equals ma or dp dt. I am doing all this exercise to make you familiar with angular momentum and related mathematics. Let us understand this by considering an example. I will consider the example of conical pendulum, and with that I will show you a couple of things. First, I will show you that the angular momentum indeed is origin dependent, and number 2, these two are indeed equivalent. So, let us do that. Let us take the example of conical pendulum. This is a nice example to illustrate the angular momentum concept and its derivative. A conical pendulum is nothing but a regular pendulum with a rod, rigid massless rod of length L, pivoted at a point here, but instead of moving in a plane, the bob goes in a circle. It is going around in a circle, and this rod makes, say, the angle theta with the vertical. Let me call this point pivot point O, and let this point where this vertical line meets the plane in which the circle is made, let me call this A. Because of the symmetry of the problem, I am going to use cylindrical coordinates that we learned in our second or first lecture to describe the motion of this bob. of mass m. It is moving around in a circle. Let this be the origin to start with O. So, first case I take O as origin. In that case, the r vector for the ball is going to be given as L sin theta, this is L sin theta times r. Remember, r unit vector is the radial unit vector in cylindrical polar coordinates, minus L cosine of theta z. Let me also say that this bob is moving with velocity v in the circle. V is always in phi direction. So, velocity v is equal to the magnitude v times unit vector phi. Those of you who have forgotten, let me remind you, for a given origin, the distance in the plane of x and y, the distance is given as r, then this u vector is r unit vector, vector perpendicular to this is a phi vector, and vector z is your z vector. So, in xy plane I am using planar polar coordinates, and z unit vector is z unit vector. So, these are given as r and v, and now let us calculate the angular momentum for the conical pendulum. Let me again remind you, this is my conical pendulum. The bob is moving around in a circle with velocity v, is going in this direction. This is origin O, and we have written r is equal to L sin theta r minus L cosine of theta z. V vector is v phi. This is the bob. This is where point A is, and therefore, the angular momentum L about O is going to be m L sin theta r minus L cosine theta z cross v phi. R cross phi is z. So, this comes out to be m v L sin theta z, and z cross phi is going to be minus r. You can check that. So, this is going to be plus m v L cosine theta r unit vector. Therefore, at any given point, let me make it again, at any given point, say here, the angular momentum has a component in the z direction, m v L sin theta, and in the r direction, m v L cosine theta, and therefore, you can see that the angular momentum is going to be something like this, with this angle being theta. This magnitude is m v L, and this angle is 90 degrees. When you work it out, you will see, after all, this is r cross v, so it has to be perpendicular to r, and then from these components you see this is the angular momentum. So, what we have learned by calculating angular momentum about this point O for this bob is that it is perpendicular to this, and its magnitude is m v L. This component has in this direction and a component in this direction. As the bob moves around, the r unit vector changes, and therefore, this component changes direction, whereas the vertical component remains constant. So, let us understand the horizontal component, which is m v L cosine of theta, keeps rotating, and the vertical component remains constant. You can already sense what dl by dt is going to be. So, dl by dt, L about O, is going to be d over dt of m v L sin theta z plus m v L cosine of theta r is derivative. In this, m, v, l, theta, z all are constant. So, this derivative is 0. In this m, v, l, theta are constant, but r unit vector keeps on changing. And if you recall from first or second lecture, dr over dt is nothing but omega in phi direction. And therefore, I get dl o dt as m, v, l cosine theta omega, and we will see what omega is in phi direction. This you could have also checked because this vector is rotating in this direction with angular frequency omega, therefore, the change has to be mvl cosine theta times omega, right. I mean, this is when it moves here in omega times t time, this change is roughly mvl cosine theta omega t. You divide by time and you get this answer. So, what we learned from this is if I take this conical pendulum, which is moving like this, dLO dt is equal to m v l cosine theta. Omega is going to be velocity divided by this by radius. So, velocity divided by L sine theta in phi direction, which is m v square cotangent theta in phi direction. Is that equal to tau? Let us do that. If I calculate the torque about this point, again r is nothing but L sine theta r minus L cosine theta z cross the force. One force is mg and the other force is tension T. Tension T you can see is parallel to r. It does not contribute to the torque, but nonetheless let us write this. Tension T has a component, since this angle is theta, is going to have a component T cosine of theta in z direction minus T sine theta in r direction, and I have a minus mg in z direction. You calculate all this and you are going to get r cross z. R cross z gives you minus phi, and therefore, you get mg L sine theta in phi direction, and everything else drops out. You can work this out very easily. So, what we learn now is that this quantity, which is dl dt, and this quantity, which is torque about O, must be the same, and therefore, we get m v square cotangent theta is equal to m g L. Let me see, it was mg L sine theta, mg L sine of theta, both were in phi direction. M drops out, and therefore, we get v square cotangent theta equals g L sine of theta. This is what we get. The maximum I can get from this is theta as a function of v and gl. So, again I raise the question, is dLO dt equivalent to f equals dp dt? The answer seems to be no, because only thing I am getting from here is the angle theta, whereas f equals dp dt also gives me the tension. Let us see that, and then we will understand it better. So, when this bob is moving in a circle like this is the tension T in the rod, this is mg, this component of T provides a centripetal acceleration, and therefore, T sine theta must be equal to m v square over the radius of the circle, which is L sine theta, and T cosine of theta must be equal to mg. We get two equations here, and therefore, we can solve them to get two quantities, that is theta and tension both, whereas when we are applying dl by dt equals tau, we are getting only one equation. The reason is that when you take cross products, some components drop out. So what is the way out? Well, let us first solve this. So from here I get t equals mg over cosine of theta, and when we substitute it in this equation, we get mg over cosine of theta equals mv square over L sine theta, and there was a sine theta here also. M drops out, and therefore we get g L sine theta equals, let us see what it was, g L sine theta equals v square cotangent theta. An equation that we had obtained earlier. However, these equations also gave me t. To find t using the torque equation, what I have to do, I have to find another equation, and that equation comes if I take torque about this point. Earlier we took torque about this point, angular momentum about that point. Now we are going to do it about point A. So let us again see, if I take A as origin, then R with respect to A is going to be equal to L sine theta, that is this distance L sine theta in the R direction, and velocity is nothing but v phi, and therefore angular momentum about A is going to be m v L sine theta, R cross phi is z. You see, when I take angular momentum about point A, only the vertical component remains. The horizontal component has vanished, and therefore when I take d LA over dt, everything on the right hand side is constant, and therefore this comes out to be 0. If that is the case, torque about point A must also be 0, and let us figure that out now. So what we have learnt, if I take L about point A, I get d LA dt is equal to 0, and this also must be equal to torque about point A. This is the tension. Let us calculate torque about point A, and I am using a strictly mathematical definition, R cross F. R is nothing but L sine theta in R direction cross F is nothing but T cosine of theta in Z direction minus T sine theta in R direction minus mg in Z direction. R cross R is 0, and therefore when I take torque about A, I get T R cross Z is minus phi, T cosine of theta minus mg times L sine theta in minus phi direction, and this must be 0 because dLA dt is 0, and this gives me T cosine theta minus mg is equal to 0, or T equals mg over cosine of theta, which is the same result as I obtained from the Newton's second law, direct application, F equals dP dt. So what we conclude is that dL dt is equal to tau is absolutely equivalent to dP dt equals F. The only subtlety is that in applying this, I may have to take torque and angular momentum about two different points. Having learnt that dL dt, although for a single particle, is equal to tau, now we enunciate the principle of the conservation of angular momentum. And that tells you if tau is 0, this means dl dt is 0 or L is a constant. You are already familiar with the use of this condition in the previous in maybe your lectures in 12th grade. Let me just show it to you. You are all familiar with Kepler's laws, and one of them is when the earth is moving around the sun or any planet is moving around the sun in equal time, they cover equal areas, and this is nothing but a manifestation of the conservation of angular momentum. Let me show you how. You see, if I take this sun as the origin, the force is always directed towards the origin, and therefore tau, the torque r cross f, because r and f are parallel, is 0, and therefore the angular momentum must be conserved. Now, you see, in this case the velocity at any given point, recall your planar polar coordinates, could be in r dot direction and perpendicular to this. So, velocity in general is r dot r plus r phi dot in phi direction, and therefore angular momentum is r cross v. V is r dot r plus r phi dot phi times m, which is equal to r cross r is 0, m r square phi dot in z direction. M is a given mass for a given particle, r and phi dot keep changing, z is a fixed vector. So, therefore, dl dt is equal to 0 implies that d over dt is of r square phi dot is equal to 0. And you can see that this r square phi dot is nothing but r square phi dot is equal to 0, r square phi dot therefore is a constant, and r square phi dot is nothing but rate 2 times the rate of area sweep. That is, given in r, this area you can see is roughly r square delta phi in time t divided by 2. This is r, this is r delta phi. So, the change of area in time delta t is r square delta phi divided by 2, divided by delta t, you get r square phi dot over 2 as the rate of change of area, and constancy of this implies constancy of rate of area sweep. So, the Kepler's second law, which says that the radius vector in a planet's motion sweeps equal areas in equal time, is nothing but a manifestation of the conservation of angular momentum. This becomes a powerful tool to solve problems involving angular momentum, as we will see in the examples as we go along. Having done all this for a single particle, I am now going to move to many particles, because after all, when we deal with a rigid body, it consists of many different point particles. So, now we are going to go to make ourselves familiar with angular momentum for a system. When I say system, that means many particles of particles. So, what we are going to consider is there are many different particles given, and by definition angular momentum is going to be the sum of angular momentum for each one of these particles, where I runs from 1 through n, 4, 5, 6, there may be n particles, 7, 8, 9, 10 and so on. So, this is nothing but summation m I, that is mass of the ith particle, m1, m2, m3, m4 r I cross V I. That is it. L total is nothing but summation over m I r I cross V I. We can use this definition now to relate the total angular momentum to the angular momentum of the center of mass and plus angular momentum about the center of mass. Recall from our previous lectures where I was talking about center of mass, and I kept on emphasizing the center of mass is a very, very important quantity, and we will use it again and again, and you will see again in rigid body dynamics it becomes a very central concept. So, let us now write L total, which is equal to summation I m I r I cross V I as summation I m I. Let me write r I as, suppose I will just make a 2-dimensional plot. This is the center of mass of a distribution of particles. I will call center of mass coordinate RCM, and the coordinate of a point particle, ith point particle with respect to Cm as r I prime. So, this is r Cm, and with respect to this the point is given at r I prime, and this is r I. Similarly, the velocity would become v of Cm plus v I prime, where, let me write explicitly, r I prime is coordinate of point I with respect to the center of mass. V I prime is the velocity of point I with respect to the Cm. So, what we get is, given a distribution of particles, L total is equal to summation I m I r Cm plus r I prime cross V Cm plus V I prime, which I can open up and write as summation I m I r Cm cross V Cm plus summation I m I r Cm cross V I prime plus summation I m I r I prime cross V Cm plus summation I m I r I prime cross V I prime. Look at this term, second term, RCM is common to all. So, this can be written as RCM cross summation I m I V I prime. Similarly, look at the third term, VCM is common. So, this can be written as summation m I r I prime cross VCM. A minute's thought will tell you this is the total momentum with respect to the center of mass, and that is always 0. Similarly, this is the coordinate of the center of mass with respect to the center of mass, that is also 0. So, these two terms drop out. What I am left with is, therefore, that L total is equal to summation I m I r Cm cross VCM plus summation I mi Ri prime cross Vi prime. Again, this is a common quantity, so this is only summation mi, which is the total mass RCM cross VCM, plus this is nothing but coordinate with respect to center of mass, velocity with respect to center of mass, therefore this becomes nothing but L about Cm. And this quantity is nothing but as if there is a massive particle of mass m moving with velocity Vcm at distance Rcm. So, this is nothing but the angular momentum of center of mass, and therefore, I can write L total as equal to L of Cm plus L about Cm. This is a general result. Irrespective of whether a body is rigid or not, so you see we have not used the rigid body condition anywhere, the total angular momentum of the body is going to be a sum of the angular momentum of its center of mass plus angular momentum about the center of mass equals L Cm plus L about Cm. And you can see if total momentum of a body is 0, that is m Vcm is 0, this implies L equals L about Cm, and therefore, in that case the angular momentum of the body, no matter where I take it from, is independent of the origin, because this has always come out to be L about Cm, but this is only because the total angular momentum, of the center of mass is 0. In general, this is the result. You can see this is also a result which depends on the property of the center of mass, that is summation mi Ri prime with respect to center of mass is 0, and similarly summation mi Vi prime is equal to 0. So, this decomposition cannot be done about any arbitrary point, that is I cannot say L equals L some point O prime plus L about that point O prime. It is only with the center of mass, because center of mass satisfies these two equalities, that I can decompose the angular momentum in this manner. This must be kept in mind. So, what we see is that L is equal to L Cm plus L about Cm. Let us take a simple example of it. Let us take a bicycle wheel rolling on the ground. If it is rolling, this point is not moving instantaneously, and therefore, if it is rolling with speed v and its radius is r, I have omega equals v over r. So, I can consider this motion as if the center of mass is translating with velocity v, on top of it this body, let me just say this is point A, point B, this whole thing is translating with velocity v, and on top of it with respect to center of mass this is moving with omega equals v over r. So, that instantaneously this point is at rest. So, the angular momentum for this, if I take the origin here, this is r, is going to be, this is r Cm, this is v Cm. So, you can see right away that L of center of mass is going to be m r v Cm, where r is the radius, r Cm cross v will give you only this projection, and L about Cm, this is going to be in the direction perpendicular, r cross v is going to be perpendicular going into the page. I am not worrying about the direction right now. L about Cm, since this is rotating like this, is also going to be m r v Cm. You can calculate that, and therefore, with respect to O, the angular momentum is going to be 2 m r v Cm. On the other hand, let this be the ground. If I shift my origin here, let us call it O prime, say by a distance r prime, then LCM is going to be equal to m r plus r prime VCM. However, L about Cm is going to remain the same, and then if you sum the two, you get L about O prime. This fact that L about any point is equal to L Cm plus L about Cm also gives rise to something known as the parallel axis theorem in relation with the moment of inertia. I am sure you have heard of this theorem, but we will come back to it later when we do rigid body dynamics. Right now we are trying to make ourselves familiar with angular momentum. How about the dynamics now? How about dl? I am dropping the suffix t right now. dl dt for a many body system. Let us work that out. Recall, when we are doing the momentum change for a many body system, we had this as d over dt summation mi ri dot, which had given us mi d 2 ri dt square, which was nothing but summation over fi, where fi, that is on ith particle, the force was nothing but the external force, that is something I apply externally, plus the force j not equal to I on ith particle due to other particles. And we had shown then, and that is how we came to center of mass motion, that this summation over I and j gives me 0 if Fij, the forces between the particles, satisfy Newton's third law, that is Fij is equal to minus Fji. The force on ith particle due to j is opposite and equal to force on jth particle due to I. A similar derivation now we are going to do for the angular momentum, and let us write this as d over dt of summation I mi ri cross vi, which gives me summation over I mi dri over dt cross vi, this being the velocity, this term cross product is 0, plus summation I mi ri cross dvi dt. Mi times this acceleration dvi dt is nothing but the force on the ith particle. So, this gives me summation I ri cross fi, where fi is the total force on the ith particle, that is the force including the external force plus the force due to other particles. So, dl dt for a many particle system, that is there are many particles which are interacting with each other, they may be interacting with each other, and there are external forces applied on each one of them, is equal to summation I ri cross fi, which explicitly I will write as I ri cross fi external plus summation over j, that is all the other particles applying a force on the ith particle, j not equal to I, which I can now write as dl dt equals summation I ri cross fi external plus summation ij I not equal to j ri cross fij. Recall, this term now I want to show to 0 in order to prove that dl dt equals ri fi external only. So, I can write summation ij I not equal to j ri cross fij. Since I and j are being summed over, I can interchange them and write this as summation Rj cross Fji. I have just interchanged j and Ij, I not equal to j, and therefore I can write this term summation Ij, I not equal to j, Ri cross Fij is equal to 1/2 of summation Ij, I not equal to j, Ri cross Fij plus Rj cross Fji. And if Fji is equal to minus Fij, this term becomes equal to 1/2 summation Ij, I not equal to j, Ri minus Rj cross Fij, and if Fij is parallel to Ri minus Rj, parallel or antiparallel, then this term is 0. Fortunately, in mechanical problems, most of the forces are such that they are along the line joining the two particles, and therefore this term always 0, and therefore we get dl dt for a many particle system also is equal to tau external. This is going to be our dynamics equation. As I showed in the example of one particle, solving this gives me the resultant motion of the particles. Let me conclude this lecture by saying, by getting our main results. Number 1, six degrees of freedom to describe freedom for rigid body motion. Three for translation, and 3 for orientation change. The tremendous reduction in the degrees of freedom comes because there is a constraint of two particles being at the same distance no matter what the motion is. Number 2, the dynamics is going to be described by dl dt. By dt equals tau external under certain conditions, that is, the forces are equal and opposite and along the line joining two particles, and this gives me the dynamics, and L for a system is equal to L Cm plus L about Cm, and fourth, if tau external therefore is 0, then L is a constant. That is the conservation of angular momentum. Having developed these ideas on angular momentum, in next lecture onwards we are going to apply them to describe the motion of a rigid body.